My name's Paul Sage, and I work in the Queen's University of Belfast in Northern Ireland. And it's my absolute pleasure to be in front of you today to talk a little bit about our work in computer science. The basis of the talk is, well, the title is Unmanned Aerial Vehicles or Drones in Archaeology. Are they a help or a hindrance? And before I progress, I need to explain a little bit further about what I mean by this. Every year we're challenged in computer science to come up with suitable student projects, both at an undergraduate and postgraduate level. And we strive to make the projects interesting, to get the best from the students through engagement. So when I looked at this title and I said to myself, does it say all I want to say? This talk will talk certainly about drones and how we've used them in our projects, but it opens up the talk a little wider to more novel technologies that we've deployed in developing our projects to help with student engagement. So on that, I decided to create an alternative title. I make no apologies for the logo that you see here. And really the emphasis is on not just drones, but novel technologies and how they can help as a gateway to collaboration with other departments and to engage students. So I picked the title for a deliberate reason, and I'm going to defer the explanation to that towards the end. Hopefully it will make more sense to you towards the conclusion of the talk. So just to set things in context, to say a little bit about myself, I'm a computer scientist, and I like to develop software. It's been in my blood since I was a student, and over the years I've had many opportunities to collaborate with many different disciplines over the years. I've worked significantly with engineering manufacturing and aerospace, automotive, and indeed other partner universities to develop, certainly in this project, automated material selection systems based on engineering requirements. So based on a particular set of engineering specifications to go through, and through some AI assistance to automatically select particular materials that will meet those engineering requirements. Other projects we've looked at, we've worked in medicine, both in the Gate Laboratory, which deals with modeling how people walk and the issues surrounding injuries and prosthetics. And I've worked with oncology in looking at slides and image processing associated with that to detect early instances of cancer. So continuing on, we've also had significant opportunities to work with external companies. One particular company deals with resource scheduling and timetabling for universities and other academic institutions, working at an algorithmic level on that sort of basis. But where my heart really lies is in high-performance computing. I'm going to say a bit more significantly about high-performance computing, and indeed in relation to another recent interest of mine, drones, unmanned aerial vehicles. So for the remainder of the talk, that's where I'm going to focus. I'm going to look a little bit about how I have used high-performance computing in association with mathematicians, physicists, and engineers. And I'm going to look a little bit about how we are moving towards working with the School of Archaeology and their work with drones and analysing the data that they collect using high-performance computing platforms. So, I don't want to go into too much technical detail, but I think it's fair to give you an idea of what I mean by high-performance computing and where it relates. So working with physicists, mathematicians, and engineers, we're really concerned with taking old codes that they have, maybe sitting around for many years, developed specifically for old-style CPUs that execute one instruction at a time. And the basis here is to provide an acceleration, to speed it up, to enhance the performance. So it's concerned primarily with the redevelopment of existing software. So any given task or a program, if you look at it, can be partitioned, split into a number of subtasks. So if you take this overall task here, the graphic would indicate the possibility of splitting the one task into separate subtasks that could be executed simultaneously. And it's the old adage of many hands make light work. If you can take a task and subdivide it and get these tasks computed at the same time, you will achieve an accelerated performance. That's the general basis of it. It is an oversimplification, but that's the general basis. The other part of the story is once you've decided how to chop something up or create subtasks, how you then manage that within what's called a multiprocessor environment. Many of you have PCs in front of you. You've heard of dual core, quad core, that sort of thing. What it really means is the CPUs of today all have multiple processing elements within them capable of executing their own tasks at the same time. That's just one example of a multi-core system, but there are many, from simple PCs through to Cray computers, through to network workstations. But in looking at this, see there's some additional problems associated with taking existing code and making it execute faster. It's not as easy as it seems. It requires a great degree of experience from the programmer, knowing how to carve things up or chop things into subtasks. And secondly, depending on the particular machine that you want to execute it on, some sort of scheduling of that algorithm is necessary to enhance the performance effectively. So what we've done, or have done in the past, we've used some artificial intelligence to replace or semi-replace the human programmer in assisting the task of splitting the initial problem up, and indeed of scheduling that problem on a named or chosen architecture. It is an oversimplification, but I think it's enough for now. So that's where my background as a programmer has lain over many years. So when we look at how we can attract students into this domain, and when I talk at length about multiprocessor architectures, even with students, the eyes start to glaze over. People start to fall asleep. It's not as interesting. It's certainly an intellectual challenge, and it does appeal to some people, but it's not as exciting as it could be. So what we thought is, how can we make things slightly different? How can we engage with students? How can we attract students to this? So we put our thinking caps on again, and if the physicists give me a code and say, Paul, could you accelerate this for me? Okay, we'll get a student maybe to do that. Oh, can we find a student that's interested enough? It's always a challenge. Normally you would say, well, which multiprocessor are you going to pick? You're going to pick a Cray, you're going to pick something from Silicon Graphics, or something else that's many millions of pounds or dollars worth of equipment. You say, okay, yes, we've tried that, but let's try something different. So a few years back, we opted for the PlayStation 3. And at that point, when we suggested doing that in an academic environment, apart from laughing and jokes and jibes, we persisted, and we got some equipment, and we put together a cluster of PlayStation 3 consoles. Now, everybody, or most people in the room, should be familiar with what this is. This is a games console released some years ago by Sony. Just tell you something very, very briefly about it. Sony released this. They had a very, very good attitude towards the lone programmer or the hacker mentality. They left the system open for installation of Linux, another operating system that enabled users to program software for the Sony PlayStation 3. Now, unfortunately, they backtracked on that and took it away because people were using it to hack Sony's operating system and to copy illegal games, and all sorts of problems occurred because of that. But there was a short window where it was possible to write software for this. And the reason why we chose it as a target platform for acceleration of, say, physics codes is it meets the architectural requirements that I mentioned at the start of the talk. The processor within, without going into too much detail, it's defunct now, it's gone, but it contained a number of discrete cores, 9 in total, that could run separate sub-programs simultaneously and provide an acceleration, in theory. So, what did we do with this? Well, we took some physics codes, not boring you with the detail, but it related to ion-ion collision simulation. Basically, lots of nested integrations. Okay, so we took that, said, right, let's look and see how we could accelerate this code on a Sony PlayStation 3. The outcome of this, well, yes, we were able to achieve a performance enhancement as we used more and more of the cores or the processing elements within the processor of the Sony PlayStation. We did see an enhanced performance, but big deal. You're not going to win any great science prizes by saying, I can accelerate physics codes on a Sony PlayStation 3. But that was never the point. The point was, can we attract students to our discipline of high-performance computing using a novel piece of equipment that attracts their attention, gets them fixed on it, and interested from the outset? So, in addition to achieving some good science, 2 impacts that we would like to consider. A research impact. Yeah, there was a research impact, all right. We raised the profile of what we were doing, which is never a bad thing. Any exposure is a good thing, especially when you're looking for money. We also had a few raised eyebrows, especially when we went to conferences and said that's what we were doing. But very quickly, when we realized we could do some real science, the laughter dissipated. But the bigger impact, and more importantly for me as an educator, was it appealed directly to what's called the PlayStation generation. For 2 reasons. Any time that we went into a hall to exhibit our research projects and potential projects to come, and any time we put a Sony PlayStation 3 down, we had all the people. We had them queuing up to find out what we were doing. The PlayStation generation. It appealed directly to what they were using themselves and proved to be invaluable as a tool for recruitment. Aside from the science, which was okay, it proved to be very, very good indeed from that point of view. From a research point of view, it got people started down a road for postgraduate diplomas and PhDs as a result of an initial interest in a machine they had at home that they played games on, that they could do something directly with themselves. That's what a computer scientist wants to do. They see a piece of equipment, they see a piece of technology, and immediately you'll say it to yourself, can I program that? What does that mean? Is there a way in for me to change its behavior, to interact with it programmatically, to get it to do what I want? The Sony PlayStation 3, for a time, was just that machine, and it did improve to be very, very invaluable. A good trick, a good game to play. So, we did that with the physicists and the mathematicians, and we're always, as educators in Belfast, looking for new technologies to encourage more students to work with us. So having an interest in drones, I'm sure most people know what a drone is. You can buy them as a toy, play with them, but the drones I'm talking about are far from toys. They are serious pieces of equipment. They're essentially flying robots that are programmable in the simple sense. In other words, you can say what it should do, where it should do it, and how far it should fly autonomously. You can decide to send it on a mission, taking several pictures on its way and returning to you without any user interaction or control. And of course, you can control it yourself if you wish. That aspect of control, that ability to interact with a device, appeals to the computer scientist. We can programmatically interact with the applications for controlling drones, both in the handheld sense, in the mobile phone sense, and in the desktop sense, but we can also interact directly with the sensors and computers that are on board these systems themselves. We can get some significant degree of control. So just to say something about how we're trying to replicate the PlayStation 3 success in a slightly new way using a different technology. We've chosen drones. But not only that, we've chosen the archaeologists to work with. Archaeologists at Queen's are big users of drone technologies. There's a picture of a drone. Just to say something a bit more about what we mean by a drone, they're also referred to as unmanned aerial vehicles. They're guided by GPS systems. They can be flown by a person, or as I mentioned earlier, they can be programmed to go on a mission. And it's this mission control that's of interest to the archaeologists. Archaeologists like drones for survey purposes. They like to view ground from the air, looking for evidence of ancient man-based activity in the ground. So they use for this a range of multispectral imaging devices from the standard visual image that you and I would look at, through thermal imaging, and they also use something called LiDAR, which is a laser that emits a laser beam many times a second to produce a 3D model of the environment in which the device is deployed. And they like now to do that from the air, where previously they were doing it solely from the ground. Why are computer scientists interested in drones? Pretty much the same reason why we're interested in PlayStation 3s, because we can program them. We can bend them to our will. Again, with the general theme of attracting good students to interesting projects, we've gone down the same route as we did with the PlayStation 3 deployment. So what did we actually do? What's actually happening? Well, we have two projects on board at the moment. One that deals with flight planning. I mentioned a moment ago that you can program a drone to go on a mission. A mission consists of a series of places to go, controlled by GPS. And at each point that you tell a drone to go, you can say, point directly down and take me a nice high-definition image. So in doing so, if you can imagine an area that could be surveyed, not unlike the image on the left, where you can split the area into a number of zones, and you can program a mission to say, visit each one of these squares in turn, and take a nice high-res image for me. And then they're merged together to get a super image at the end of the day for subsequent processing and analysis. So we're working on systems that deal with scheduling such activity, so you can see the arrow following through a sequence of points to achieve a completed survey. This technology is also used in combine harvesters to bring in the harvest in the summer. A lot of the combine harvesters are GPS driven, and the person that sits in the cab is just there to watch and make sure everything works okay. So it's the same technology, the same idea. But within this project, what we're particularly interested in is maximizing battery efficiency. There's a limited lifespan on a battery, so you have to say, if I want a survey done, based on what I would like to do and the capacity of the battery, here are the factors involved, the amount of ground we want to cover, the resolution of image we want, the camera capabilities, what can be done. But most effectively, we're interested in the effect that the wind would have. The more the wind blows, the more power is drained from the battery of these devices. So what we're looking at is two forms of mission control, if you like. One that just takes a general reading of wind and provides what it hopes to be an optimal path to provide a survey. But we're also looking at another type of survey that takes real telemetry of changing wind conditions, and using AI will change the direction of the drone from point to point based on prevailing conditions. So that's what we're interested in doing at that level. The other project that we're looking at is post-processing of data collected through surveys, looking for features of interest. So I don't know if you can see these rings. Here we have an example image, and you can see a number of houses surrounding this area that appears to have a number of concentric rings about it. What it actually represents is a ring fort in the suburbs of Belfast that have been built around. It's long been known that this exists, but it indicates the sort of things that the archaeologists are looking to see from the air. Any sort of straight line in the image, any sort of circle or square end is indications of human activity. And part of the image processing is to look at that and see if it can be identified easily. Where does the computer scientist come in? Well, we look to use, again, back to the high performance computing, we look to deploy these multiprocessors to make things go quickly, to the extent that we hope to be able to survey and produce results while the drone's still in the air. Do it live. In other words, export the data captured live and see the outcome very, very quickly. Export it to the cloud, get the work done, and see it overlaid on a PC live. That's what we hope to do. We haven't done it. That's our aspiration. Okay, so I'm back to the original question. This is by way of conclusion. It said UAV drones, a help or a hindrance? A help or a hindrance to what? Does it help me as a researcher? Yes. Does it help me attract students? Yes. Well, let's say a bit more about that. Gaming technologies using the PS3, did it help? I mean, what student doesn't want to hack their console? You tell me. We had them lining up at the door for projects. Most students good, willing to engage and participate. UAV drones, we're experiencing a similar level of interest for projects. What student doesn't want to pretend to be Indiana Jones and fly robots? So, again, I'll refer back to say yes. My experience has been very, very helpful to move aside from the standard, to take a chance on a device or a technology that nobody else would look at or touch, in the sense, because it has yielded significant results in terms of the students that we've attracted. It also has had significant benefit in the classroom when we're teaching programming at that level. Instead of teaching theory of multiprocessor programming, we can say, here's a PlayStation 3. That's the architecture we're looking at. They all can relate to it, and it makes the information more amenable to them. So guys, that's pretty much it. That's all I have to say. If any questions, I'd be willing to